Good day and welcome back for part one of our discussion on trig substitutions. We are continuing on our investigation into the various techniques of integration. And this current technique, trig substitutions, directly builds upon our previous discussion of trigonometric integrals, as each one of these substitutions will result in a trig integral, which we will need to solve. And as we continue on this discussion of techniques of integration, it's really important to pay attention to why we would use one method. That is, what is the mental thought process that we go through? And currently we've seen for things like, say, substitution and integration by parts, there's kind of defining characteristics or certain types of integrals that are conducive to the given method of integration. Trigonometric integrals we can recognize very quickly and efficiently because they involve trig functions. In terms of trig substitutions, we're going to be looking at our integrand for quantities of the form a squared minus x squared, a squared plus x squared, or x squared minus a squared, where we're not able to apply our previous methods. So substitution and integration by parts would not be able to help us solve the integral. Now, a trig substitution is a specific type of substitution which I would describe as being a reverse substitution. So let me begin by reminding you of our technique of substitution, which I'm now going to refer to as a direct substitution. When we encounter an integral of the form f of g of x times g prime of x, our intuition is we might see a function derivative pair. If we were to set u to be g of x, then du is g prime x dx. And the integral can be written solely now as a function of that variable u. And I think of this as being a direct substitution. But we could also reverse this process, that is, start off with an integral of the form on the right and make a substitution to get back something that looks like what we have on the left. So for example, if we started off with an integral of the form f of x, it is perfectly reasonable to substitute with something like x equals g of t. And if we're letting x be equal to g of t, that means we need to get the entire integrand, including the dx, in terms of t as well. So we would replace the dx with g prime t dt. And this allows us to rewrite the integral as f of g of t times g prime of t dt. And as we will see, a trig substitution will take on this form. So let's look at two concrete examples, maybe illustrating the difference between these two substitutions. So the first example is an old, familiar problem. If we are asked to evaluate this indefinite integral in Calculus 1, our intuition immediately would be that to choose u to be this inside function, 1 minus x squared. So du is minus 2x dx, or minus 1/2 du is x dx. So we can immediately rewrite this integrand solely in terms of u. The x dx becomes minus 1/2 du. So we'll pull the constant out front, and what we're integrating is the square root of u. And in terms of antiderivatives, this is quite reasonable. The square root of u is really u to the 1/2. 1 plus 1/2 is 3/2. So we have 1 over 3/2, which is 2/3, u to the 3/2. And finally, as usually is the case, we resubstitute. So we have a minus 1/3 hanging around out front, 1 minus x squared quantity to 3/2. And this is the standard type of substitution we are familiar to working with. Now, a slight modification of this problem. Let's remove the x and evaluate this integral. Now note it may seem as though we would make it easier by deleting this term x, but it turns out that actually makes the integral more involved. Because without that x, we cannot apply a direct substitution as we've done previously. What we're going to do is apply a reverse substitution. And I'm going to try to give you some intuition as to where we're going with this. So let's just make an observation to the side. The function we are integrating, we're thinking y is the square root of 1 minus x squared. And if we square, we could really rewrite this as x squared plus y squared equals 1. And what I want us to think about for a moment, is there any other relationship we've seen recently that satisfies an equation similar to this? And hopefully what you're maybe thinking, and if not you will be in a moment, this looks a lot like the Pythagorean identity, right? Cosine squared plus sine squared is equal to 1. So with that in mind, we are going to evaluate this integral using a reverse substitution. I'm going to set x equal to sine of theta, which makes dx cosine theta d theta. And note, we could really let x be equal to sine or cosine. I am choosing sine purely for the convenience of not having an extra negative sign come up in the dx. Now what we are able to do is rewrite our integrand by substituting in those quantities. So I want to make the x a sine, and dx is going to be cosine theta d theta. And the reason this is going to work out nicely is because of our observation that this is familiar to the Pythagorean identity. 1 minus sine squared is equal to what? It's equal to cosine squared. So underneath the square root, we have cosine squared of theta. So this would be the integral of the square root of cosine squared times cosine d theta. And if we simplify this, the square root of cosine squared, we want to write as cosine times cosine. And I am going to make one kind of just small observation. You know, typically when we see the square root of something squared, what we would get back is its absolute value. And it turns out that's not going to be something we are going to have to worry about in this course. There's going to be an underlying assumption, and it's just going to restrict where the theta values lie. That is, cosine of theta is bigger than or equal to 0 as long as the theta value is chosen to lie between minus pi over 2 and pi over 2. So with that observation out of the way, let's just kind of continue on evaluating this integral, kind of just one small step at a time. So now we have the antiderivative of cosine squared. So as I mentioned previously, using what we are going to refer to as a trig substitution turns this integral into a trigonometric integral, our previous topic of interest. We will evaluate and then resubstitute. Recall, in order to evaluate the integral of cosine squared, we need to rewrite it in terms of what is hopefully now that familiar half-angle identity. And that identity is cosine squared theta is 1/2 1 plus cosine of 2 theta. And I will immediately pull the 1/2 in front of the integral. Now we can antidifferentiate individually each term. So I'll leave the 1/2 hanging around out front. We're antidifferentiating with respect to theta. So theta plus 1/2 sine of 2 theta. And note, the last step in our process is we need to resubstitute. That is, our final solution should be in terms of that original variable x. And this is really a new part of the problem for us. So recall our substitution that we made above. We said x is equal to sine of theta. And in order to rewrite theta in terms of x, I guess one thing we could say for the theta in our solution, we could express that as being arc sine of x. So we can take care of the theta without an issue. But in terms of rewriting sine of 2 theta, we're going to need a bit more. And it turns out our standard approach is going to involve drawing a triangle. But in this case, before drawing a triangle, let me remind you of a trig identity. Sine of 2 theta is 2 sine theta cosine theta. And if you include this 1/2 in front of it, we have to be able to take care of sine theta and cosine theta. Sine theta, you're noting, is not a problem. That's simply x. We need a triangle if we want to determine cosine of theta. So when we have x equals sine theta, there is an associated right triangle. Remember, sine of theta is opposite over hypotenuse. We can use the Pythagorean theorem to determine the length of that bottom leg, the square root of 1 minus x squared. And kind of an observation that's nice to make here is this bottom leg of the triangle that we had to determine the length of is exactly this expression that prompted the trig substitution to start with. And that's almost always going to be the case, which gives us a nice double check. So now, putting everything solely in terms of x's. We mentioned that theta is arc sine of x. That next term, 1/2 times 2 sine theta cosine theta, only involves now a sine theta cosine theta after simplifying. Sine of theta is x. Cosine theta, looking at our triangle, adjacent over hypotenuse, is the square root of 1 minus x squared. And then we finish with a plus c. So just to kind of recap, based upon what we saw in our integrand under the square root, this 1 minus x squared, we used a trig substitution. A trig substitution is a reverse substitution. So once we determine x, that gives us dx. We express our integral in terms of thetas. Once we've done so, we applied the Pythagorean identity. To simplify, we evaluate the resulting trig integral, and then we draw a right triangle to resubstitute. And this is our first example of what we will now refer to as a trig substitution. And let's finish up this discussion by summarizing when and what trig substitution we would want to use. So as we are going to see, when it comes to trig substitutions, the substitution is going to be prompted by seeing some type of expression appearing in our integrand and not being able to use any of our previous methods of integration. So if we see something in our integrand of the form a squared minus x squared, where here we're thinking a is a number, the substitution we would want to make is x equals a sine of theta. And I'm going to throw out there that we just did this a moment ago. In our previous example, we had 1 minus x squared, and we made the substitution x equals 1 sine theta, or just simply x equals sine theta. When you make this substitution, you are going to have to use the Pythagorean identity, but even more specifically, you will use 1 minus sine squared is cosine squared. If your integrand contains the expression a squared plus x squared, the trig substitution that we would want to attempt would be x equals a tangent theta, And we would use the trig identity that 1 plus tangent squared is equal to secant squared. And finally, if your integrand contains the expression x squared minus a squared, that will prompt us to make the trig substitution x equals a secant theta, and use the resulting identity secant squared theta minus 1 is tangent squared. And we will continue on this discussion with another concrete example in our next video.